All right, thank you, Luke, and good day, everybody. As Luke mentioned, my name is Vincent Britz, or Vince for short, and I work in some of the development work on Flownex as well as the high-level technical support. Today, I'd like to talk about some of the applications of Flownex when it comes to turbine blade cooling, particularly when it comes to integrating a one-dimensional and three-dimensional simulation for simulating the heat transfer inside of these turbine blades. First, I'd just like to give a quick overview of the presentation. I just want to kick it off with a small introduction to Flownex, what it's about, and a brief overview of what the interface looks like. I then just want to discuss a few of the components in the rotating library. This is the library or the set of components that we like to use when modeling rotating flows in turbines in general. Then I'll be demonstrating an example, a co-simulation between Flownex and ANSYS Mechanical for the purposes of simulating blade cooling. And then lastly, I'd like to wrap off by highlighting some applications of co-simulation for the purposes of modeling blade cooling. All right, so Flownex itself is what we would call a flow network modeling systems simulation software package. It sounds like a bit of a mouthful, but basically what it is a one-dimensional network solving package. So it's software designed around one-dimensional flow elements and two-dimensional heat transfer elements, which you can use to build thermal fluid networks. This is then solved in a very similar way to CFD with governing equations or conservation equations for mass, energy, and momentum considered. And in Flownex, we actually use an algorithm called the pressure correction method. This leads to incredibly fast solution times. Steady-state solutions will be solved in the order of seconds, and transients, depending on the length of the transient, seconds or minutes in the worst-case scenario. The software itself is designed to work with many different types of fluids. So we have fluid models for incompressible and compressible fluids, as well as two-phase fluids, mixtures of gases, gases and liquids mixed together for the purposes of combustion models, as well as more advanced fluids like slurries and settling, settling and non-settling. The software itself also ships with a couple of analysis tools. So it has designer functionality, which works very similar to the goal-seek function inside of Excel. It can help when sizing components to achieve certain temperatures or flow rates, for example. It has an optimizer, which works similar to the designer. However, instead of designing for an exact value, it just seeks to either minimize or maximize a value. And then lastly, the sensitivity analysis functionality is used to vary a couple of input parameters and see the effect on other parameters inside of your system. So it's very good in the optimization stage of your design if you're looking to optimize many different variables. The software itself is both NQA1 and ISO 9001 compliant. So it's developed in a very an environment with very high quality control and quality assurance standards. It's verified for nuclear safety calculations as well, so the software goes through a very rigorous verification and validation process as well. The software was originated in 1986, started out in the nuclear industry, but has moved on from there. Well, not moved on, but kind of moved broadly outwards from there, and has many applications in the turbine and aerospace industries as well. Development of the software is still ongoing and continues like to this day. Anyways, so flow network modeling itself. Basically what this is a system model where pressure drops, pressure rises, heat transfer are taken into account by small building blocks. See them as components in the system, such as a pump, for example. The actual physics inside of that component are then modeled with empirical correlations. So it has governing equations for our conservation of mass, energy, and momentum, coupled to empirical correlations to calculate pressure rises or pressure drops inside of the system. This basically allows us to predict system responses with minimal computational effort. So we can use validated correlations and then couple them to our system solver, and in doing so get accurate system level responses for large networks or even small networks in the case of some other examples. This basically allows the analysis of incredibly large systems or incredibly like finely detailed systems, which would be otherwise impractical to analyze in a traditional three-dimensional CFD environment. The meshes would just be simply too large to run practically. And yeah, as I mentioned, the software itself is using validated correlations and fundamental theory. So it forms a hybrid or basically a semi-empirical model. Okay, the interface inside Flownex is structured as follows. It uses nodes, elements, and then boundary conditions to constrain your entire system. So nodes could be tanks, they could be cavities. Perhaps inside of a turbine you might have a small cavity between a rotor and a stator, or between a rotor and a rotor, which represents a portion of air which is not moving as much as the air in other portions of your network. Basically, sort of a dead volume inside of your system. These nodes are the points where we look at our mass and energy conservation. We then have elements inside of the system which account for our momentum conservation, and these are what we use with their pressure drop characteristics to work out flow distributions inside of large networks. Boundary conditions can then be imposed on the system. In the case of rotating flow, we can impose total pressure boundaries, static pressure boundaries, and even swirl pressure boundaries if we need to. Swirl pressure boundaries just being used to include the rotational components of the flow, as well as the pressure and temperature, for example. All right, so inside Flownex, we have a couple of different applications in terms of cooling flow or secondary flow modeling. We have the blade cooling flow, which I'll be focusing on today, but then there are also other applications when it comes to additional secondary flows inside of turbo machinery. So be this a tap-off point from a compressor stage and the routing of that flow into a turbine stage. This flow can then be modeled by a sequence of one-dimensional elements and basically solved in this one-dimensional environment. For more information on this, I strongly recommend you take a look at the cooling flow paths webinar on our website. The link is over there. And basically, this webinar discusses the applications of Flownex in modeling these cooling or secondary flows, and also shows some examples as to how the components can be used to model these, as well as some more of the fundamental theory behind the development of these components. So when it comes to modeling cooling paths, a one-dimensional or this flow network modeling approach is quite suitable because the flow itself follows a series of one-dimensional paths. So the one-dimensional flow discretization suits this very well. The body forces inside of the turbine due to the rotation can be easily accounted for in the governing equations. And due to the very fast solution times of this approach, it allows us to run extensive parametric studies to be completed in a short period of time. The typical components that we use when it comes to modeling this are rotating channels and a couple of other components. I'd just like to talk shortly about some of the considerations inside of these components and their applicability before we actually move on to the demonstration where I'll be using some of these components. So the rotating channel, for example, simply just represented by this icon, is suited for a compressible flow model. It will also take into account any choking effects. So if we ever exceed our critical pressure ratio, that will be taken into consideration, and the mass flow will then be limited. The rotating channels themselves have correlations for many different actual shapes of channels. So they can be smooth wall channels, or ribbed walls, or pedestal configurations, typically used to increase the Reynolds number of the flow and increase the heat transfer inside of those channels. So we have correlations built in for both the increased pressure drop or the increased friction factor, as well as the increased heat transfer. Inside of these components, we take into account all the body forces as well as the power transfer. So the change in the basically the radial position of our flow is going to affect the power inside of the turbine blade, and all of these powers, the power result through each of the components can be viewed as well. So you can see what effect the cooling flow is having on the power generation of the turbine blade itself as well. The channels themselves are not limited in terms of their flow orientation. The channels, we already have predefined options for radial, tangential, or axial flow, or pure radial, tangential, axial flow, but it can be very easily specified in spherical coordinates for any arbitrary angle. So Flownex will take into account the flow through that that direction of channel as well. So if you have nozzles or channels positioned at odd angles inside of a blade, we can map that angle precisely. Another component that we use very often is the rotating nozzle. This is typically used to model the exits of the cooling flow channels where the film leaves the interior of the blade and is then passed over the exterior of the blade for the purposes of film cooling. We have many different correlations for our discharge coefficient. We have sharp entry, rounded entry, chamfered entry correlations. Also taking into account the effect of the incidence angle on the discharge coefficient, as well as looking at whether or not the nozzle is best modeled with a long or short orifice theory, basically. We can also take into account arbitrary flow angles here, and all the body forces as well as power transfer is accounted for and displayed. Okay, so without any further ado, let's talk about the demonstration for today. What I'd like to do is talk about the modeling of a turbine blade. That little model that you can see on the right there is just a CAD representation of the blade. This model itself, just a small disclaimer, is not aimed to mimic actual geometry perfectly. This is a model I managed to find online on GrabCAD and is suitable for demonstration purposes. So I've assumed a couple of pressures and temperatures, but the philosophy behind it is to showcase the coupling and the interface and not look at the exact analysis of the exact results of the simulation. If, however, you would like to explore the exact accuracy of the software, please feel free to contact us. We're very happy doing any type of benchmark analysis for comparison to your own codes or to any other codes you would like. All right. In this model over here, what I'd like to do is model the cooling flows inside of Flownex using the components that I just discussed, and then model the heat transfer through the blade itself in ANSYS Mechanical. The reason that we would want to do this is because the shape of the turbine blade is very complex, and modeling that as a sequence of one-dimensional heat transfer elements would be very impractical. So to properly account for the heat transfer through the blade to the surface of the blade, it would be best to use a three-dimensional FE8 code. So in this case, ANSYS Mechanical is ideal for this. Just as a note, for the external film flow, just for this webinar, I'm just going to be using fixed bulk temperatures for the flow around it with a reduced bulk temperature for the flow at the exits of our film coolant slots. I just made this assumption just to limit the complexity of this model so that it's easier to understand. However, it is possible to link ANSYS Mechanical and ANSYS CFX and Flownex using ANSYS CFX and ANSYS Mechanical with an FSI coupling, and then Flownex couples to the codes individually. And basically we would then be able to take into account the detailed external flow over the blade, where we can include the fluid temperatures and flow rates from Flownex into CFX and use that along with the surface temperatures calculated in ANSYS Mechanical for a full detailed external heat transfer analysis. So just to clarify, for this simulation I'll just be looking at constant boundary conditions for our system with a reduced temperature in the region where we have our cooling film. Okay, so I'm just going to quickly pop across to ANSYS Mechanical and just show you the setup that I have over here. So it's the turbine blade, as I showed earlier. What I've done is I've just taken different zones for the individual parts inside of the interior of the turbine blade. I've just referred to them as row 1, 2, and 3. We then have a zone also for our inlet. So at the bottom of our turbine blade itself, we have an inlet port for our cooling flow. I've modeled that, and then also looked at the exterior convection in the region that does not have any cooling film, as well as the region that does have a cooling film. Inside of Flownex, what I've done is I've just taken a small CAD representation of what this blade would look like, just made a section view through there, and then added Flownex components on top of it. So let me just remove this quickly, just so that I can remove all the clutter. Okay, so what we have over here is the inlet port for our turbine cooling, for our blade cooling. This here is modeled using a rotating channel. What we do in this scenario is specify the length of this channel as well as the area and the circumference and the inlet and exit radial positions. Using this information, Flownex can then calculate the pressure drop through here as well as all the body forces on the fluid inside of this channel. I've coupled this using a convective or composite heat transfer elements configured for convective heat transfer, and then connected that to the wall inside of our blade here. The flow then continues through the remaining portions of the blade. I've used rotating orifices or restrictors, basically with a specified rotational speed. We then have this orifice providing a particular discharge coefficient, and then calculating the pressure drop through each of these little gaps in the turbine channels themselves. The flow through the actual channels is modeled using rotating channels again, where we specify the areas and radial positions of the inlet and outlet, along with heat transfer in a very similar way as I mentioned. However, for the zones where we have pedestals, we select the pipe hole profile as pedestals instead. For all the other channels, we've been using smooth as our pipe hole profile, and the friction factor correlation for a smooth wall will then be used. When we switch across to the pedestal correlation, we just simply need to specify some more information regarding the geometry of these pedestals. Once that's all included, Flownex can solve the flow through this arrangement, accounting for the correct pressure drop, and the heat transfer coefficients, heat transfer components have been modified accordingly as well. All right, the flow then finally flows through some nozzles up here at the top and down at the bottom. These nozzles are specified in a very similar way, where we specify the diameter of the nozzles. We can have the discharge coefficient calculated. In this case, I've chosen sharp edge entries as the particular correlation to be used, where Flownex then looks at calculating the incidence angle as well. So there are many options here to override the inputs. However, I've configured it all for Flownex to calculate with just the basic geometry specified. Okay, so for the integration between these codes, what we need to do is basically transfer information from Flownex to ANSYS Mechanical and then back to Flownex. The way in which this is done is through our mechanical coupling. That's this component over here. Information is transferred from Flownex components to this through these little dotted lines. These are called data transfer links inside of Flownex. And then once the information is inside the coupling, it's basically converted, or it's basically written into a input file for ANSYS Mechanical. So whenever you configure a simulation, you can write a .dat input file. That basically stores all of the information for the geometry, for the boundary conditions, and the solution procedure for solving that particular system. And Flownex can then modify the inputs for that according to the results from the one-dimensional flow simulation. That file is then inputted into Mechanical and solved in batch mode. Mechanical then generates a results file, which Flownex then reads and updates the values inside of the one-dimensional environment, executes another iteration in the flow environment, in the flow side, and then this process repeats until the system converges. So basically how that works is we take all of our components here and then map them across to the different zones in which we've specified our boundary conditions. So inside of ANSYS Mechanical, if you turn on the beta appearance features, you're actually able to get ID values for each of your boundary conditions. Using this information, we can then specify exactly where the information needs to be transferred from Flownex. So, for example, row 3 was number 38 inside of ANSYS. You can see that over here. Information is then transferred from Flownex to the load vary. This is just used as the prefix for a temperature, the identifier, which is 38, and then the actual tensor position 2,1,1. This is standard across all of our inputs, and this basically is the prefix that Flownex is looking for inside of the ANSYS input file, and then replaces the value that follows that prefix with the result from Flownex. So basically what this component does is it modifies that input file according to the specifications we give it here. It then reads the results files. We specify the names of the results that we're looking for, and then Flownex is able to transfer that information back into our flow network over here. Okay, so let's just run the simulation. As it runs, you should notice over here there's a small little additional application opening. This is ANSYS Mechanical running in batch mode. It doesn't produce any type of GUI or anything like that, just to improve the solving speed. But basically what we're able to do is have the ANSYS mechanical solver running in the background, just in batch mode, to provide all the necessary calculations for the conduction and convection in the exterior and the interior of the turbine blade. What I've done over here is just plot some of the results inside of the simulation. So I'm looking at plotting I'm looking to see if the two systems have two simulations have converged. So I've plotted an arbitrary mass flow. In this case, it's the mass flow through the inlet port, and then also the temperature of one of the exiting ports over here. In doing so, what I can do is try and visualize the changes in these results. In a more industry-driven application, we would look at a combination of these results to try and establish whether or not the system is converged. But in this scenario here, simply looking at a temperature and a mass flow should be a relatively good indication as to whether or not the two systems have converged. So after just a few iterations, we see the change in our simulations becoming most negligible. So we're then able to stop our simulation. Just wait for a second. And then view all of our flow results here in Flownex. So we have result layers. These are basically just graphical representations of some of the results. I've just configured this one to display the temperatures of the fluids in each of these flow components. And we can see a rough indication of what the temperature distribution inside of our turbine blade is in terms of the fluid temperatures. We're also able to look at many other variables, such as the flow rates through the individual channels or the flow rates through some of the restrictors or nozzles individually. When it comes to the three-dimensional results, that's very easy to look at inside of mechanical. We simply import the results file that Flownex just mechanical generated when it was running in batch mode. So I have just selected the location of the files that Flownex was executing, or that mechanical was executing. We then simply open the results file, choose the correct unit standard that we were using, and then we're able to view the results in our three-dimensional environment as well. So we can look at the temperature distribution across the entire blade, and then see particular areas where we have hotspots. This would be from a three-dimensional point of view, and we can then look at sectioning our blade and looking at some of the more internal results where our cooling flow starts to play a more important role. Okay, so that basically covers the integration of these two codes. From the results side, as I mentioned, we have access to our velocities, pressures, temperatures, flow rates, and because we're using a compressible model, we can also see we can also account for the effects of choking inside of our components. We can also visualize the heat transfer coefficients. So the individual heat transfer coefficients from each of these convection components is then transferred to ANSYS mechanical. So we can look at those individually and see how the heat transfer coefficient in each region is varying. We can also look at the power transfer, as I mentioned, and see what effect this has on the total power transfer or total power extraction of our turbine. All right, the mechanical results, as I mentioned, are then just simply imported using that results file and then can be displayed inside of ANSYS mechanical directly. Okay, so in terms of applications, using both a 1D and a 3D code together provides high levels of accuracy and detail at a component level. So we're able to model the convective heat transfer, conductive heat transfer through the blade by basically having a finely discretized mesh in our solid and then accounting for the conductive heat transfer through there. So we're able to capture the actual geometry of that blade. We can also then look at decreasing our solving times by modeling the flow internally inside the blade. So as this flow is mostly one-dimensional, this model of the flow network, this flow network modeling approach, is ideal for modeling these flows, as we can include all of the effects, all of our body forces, as well as all of the standard correlations for our friction factors and our heat transfer coefficients in these particular geometries. So we can capture that flow particularly well and then transfer that information to our 3D simulation. So we can have the increased solving time of the decreased solving time of the 1D code with the accuracy of the 3D code. As I mentioned, we can also then look at modeling the three-dimensional flow on the outside using something like CFX for a complete model of the blade in its entirety. All right. So in summary, Flownex itself is a commercial one-dimensional, basically network solving tool. It uses conservation equations for mass, energy, and momentum with some basically proven correlations for the individual pressure drops inside of our system and heat transfers. It has a user-friendly GUI. Constructing networks is quick and easy, and results are easily accessible. These results can be exported very easily through many different interfaces, such as Excel or text-based interfaces if you would like, and also be linked to third-party programs for co-simulation. So it can be transferred to CFD codes as well as more structural thermal codes. The library employs standard correlations that are particular to specific industries, in this case, particular to the gas turbine industry, for both pressure drop and for heat transfer. We have many components for modeling components beyond just the turbine blade itself. So we have components for vortices, for seals, cavities, nozzles, rotating gaps. I would strongly recommend that you take a look at the webinar on secondary flow or cooling flow. These explain all of these other components in a large amount of detail, and it's definitely worth taking a look. The software itself has scripting capabilities to allow users to input custom correlations. So if you have in-house correlations that are not publicly available, these correlations can quite easily be included in your model in a simple C# script. It's very easy to use and has minimal overhead code. The script can then be linked to pressure drop components or to heat transfer components to specify custom friction factors or custom pressure drops inside of your system, or heat transfer coefficients, for example. The one-dimensional architecture results in incredibly short solving times, and as a result, we can look at doing extensive parametric studies for the purposes of optimization. The software itself is continually being developed. We typically have somewhere between 2 and 3 releases per year, and the development of the software is driven by client needs. So a lot of the new developments into our turbine modeling comes directly from clients who are using the software. So we're continually trying to expand the usefulness of the code and add new features that make the code even more useful in their environments.